One of the more interesting aspects of chaotic systems, and we can demonstrate this, or I'm demonstrating this here with the Lorentz equations, is that the predictability of a chaotic system depends on where you start the system. And some states are very predictable, and some states are very unpredictable. So this is an example where we imagine we have an initial state that we don't know exactly what that initial state is. There's some uncertainty, some little error bar. And we can represent that by saying that the initial state lies somewhere in that initial ring. Look at the top left-hand diagram to start with. So the initial point lies somewhere in that initial ring. And the question is, we want to make a prediction. Maybe each little arrow represents a day, let's say. This is kind of a weather type thing. So after 10, 15 days, the system has made a transition to the other side of the attractor. But you'll see that the little ring hasn't actually spread out at all. In fact, if anything, it's actually slightly shrunk. So although, again, we don't know precisely where the final state will be, we're pretty certain that it actually lies somewhere in that right-hand wing of the attractor. So this bit of the attractor, the fractal geometry, is actually very, very predictable, even though it's a chaotic system. The top right figure shows an example which perhaps is more generic, which is that the little ring of points starts to evolve downwards, and as it gets towards the bottom of the attractor, then it kind of starts to deform into like a banana shape, sort of kind of banana shape, and then that gets stretched out. And we don't know for certain, for example, whether the true state, which lay somewhere in that initial ring, actually made the transition to the right-hand lobe of the attractor or stayed on the left. There's uncertainty. But then on the bottom here, you see an example where the uncertainty is kind of explosive. My initial point is somewhere near the bottom of the attractor, and now just things get ripped apart very quickly, and you basically got no idea whether the true system, the true state lies on the left or the right. Now, as we will see, this is generic for chaotic systems, that the predictability depends on the initial conditions. And if it's important to know whether you're entering a system which is predictable or unpredictable, the way you can find out ahead of time is to run multiple forecasts. You just vary slightly your initial conditions, and you look to see, are all the forecasts diverging in state space, or are they all sticking together? And this is what I worked on for a number of years with colleagues. I don't know if my colleague Roberto Buizza is in the audience or not. Yes, here he is. He and I worked on this for a number of years at the European Centre for Medium-Range Weather Forecasts, kind of putting this idea into kind of weather forecast reality. And what I'm showing you here is three examples of which kind of illustrate the three different phases of the Lorentz attractor, but for the real world of weather prediction, and we're looking specifically at extreme weather and tropical cyclones or hurricanes in different parts of the tropics. And this top one is of a forecast about a week ahead of a cyclone called Sidr, which, as you can see, was predicted with a pretty high probability. Most of the tracks are going up towards Bangladesh, of hitting Bangladesh. So clearly, if you were, leading some kind of disaster preparedness in Bangladesh, you would have a pretty good heads up that this was a very high probability type of event, and indeed, that's exactly what happened. The middle one is the famous Hurricane Katrina, which hit New Orleans in whenever it was, some years ago now. And again, we're looking at these ensembles of hurricane tracks about a week before landfall. And you can see, actually, at that range, there was clearly a possibility that Katrina would hit New Orleans, which is halfway along the Gulf of Mexico there. But it was by far not clear. It was not perhaps the most likely scenario at that range. So if you were governor of New Orleans, I mean, or indeed a national disaster preparedness, you wouldn't perhaps put all your eggs in the basket of putting all your resources into preparing New Orleans, because there are other places at risk as well. But as you got closer to the actual time when it made landfall, then it would have been more obvious New Orleans was at risk. And the bottom one, which is a bit like that explosive instability in Lawrence, is called Hurricane. It was a thing called Hurricane Nadine, where you literally didn't even know whether it was going to go east towards Europe or west back towards the Caribbean. Now, it's turned out that this has been really kind of pivotal in the way in which disaster preparedness agencies and humanitarian agencies now act. And it's created a program called Anticipatory Action, which is really changing the way things work in the humanitarian agency. Because in the past, as I'm sure you're all aware, these agencies didn't have like infinite amounts of money. They had a limited amount of money, and they couldn't afford to put a lot of resources into events which may not happen. And typically then what tended to happen is they went in after a hurricane had hit, supplying food and medicine and shelters and water and so on to people afflicted. But after it's hit, often the logistics are really difficult, and it's often, when you have outlying islands and things, it can take a week or more for people to get desperately needed food and medicine and so on. So the idea behind anticipatory action is you send this stuff out ahead of time. It sounds obvious, but the question is, how do they ensure that their limited funding is used efficiently? And the answer is now, with these ensemble forecasts, they have objective estimates of probability, the probability that an extreme event will hit. And they will have done a cost-benefit analysis prior to the event occurring, which would say when the probability exceeds some threshold, some predetermined threshold, let's say it's 70% or something, 80%, then we send the supplies in ahead of time. So in other words, these ensembles, as I say, driven by, motivated by very idealized models like Lawrence's model, have completely changed the way in which humanitarian organizations now are able to provide emergency supplies ahead of time. And they can do it in a cost-effective way. They're not sort of wasting resources when things don't happen. They have an objective means of deciding because they have objectively estimated probabilities. So in the case of Cider, the probability would be around 80% at 7 days. For Katrina, obviously, the probability of hitting New Orleans at that range is much less, and probably that wouldn't have triggered anticipatory action for New Orleans. But in any case, this is kind of changing the way things have done. So that's one application of chaos. I'm just going to come back to before I leave sort of weather and climate, I'm going to come back to this magnetic pendulum just to illustrate a concept, I suppose, because one hears from time to time from, let's say, those who are skeptical about climate change, the argument, well, if the weather is chaotic and you can't really make kind of reliable predictions more than a few days ahead, how can we possibly ever trust a century-long forecast that the climate is going to change? And my answer to that type of assertion, if you like, is to say that you haven't really understood the nature of climate change. So I'm going to try and illustrate the point. I don't know how, as I say, the team put this together this afternoon, so we'll see if it works. So the idea here is we let the pendulum go, and what we're going to do is imagine each magnet kind of represents a possible type of weather. And some of them perhaps represent warm types of weather, others represent cold weather, perhaps some are dry, some are wet. And this would be our normal sort of climate. The climate oscillates around these weather types in a very irregular and hard to predict way. But nevertheless, if this thing were to keep going forever, we could calculate the statistics. How often was it near one of my warm weather states, or how often was it near one of my cold weather states, and so on. We'd build up a probability distribution, and that probability distribution would be very robust. The longer we could run the pendulum for, the more reliable and definitive would be these probabilities. So what's happening with climate change is that we're tilting the table. We're emitting carbon dioxide, and that's making this thing now operate on a surface which is no longer flat. So when now with my tilted surface, I look at the statistics of these different types of weather, we see it's no longer the same as when it was flat. The warm weather states have now become more populated, more likely a priori. So this is a chaotic system where we've imposed a kind of external forcing, and the external forcing, the system is still chaotic with the imposed external forcing, but the statistics of the system have changed, and the statistics have changed in a completely predictable and robust way. So that is the nature of climate change, or trying to estimate climate change. It's trying to estimate changes in the statistics of weather given our emissions of carbon dioxide. So if you're ever confronted by somebody, the weather's chaotic, you can't possibly forecast 100 years from now. We're not doing an initial value problem. We're trying to estimate the changes in the statistics of weather given a kind of a change in the from a level playing field to an unlevel one. By the way, this example of the ensembles and the anticipatory action, this is quite a nice, I think, example of how in meteorology we use a hierarchy of models from some rather idealized ones. The one that Lorentz discovered was a very idealized model, right through to the very complex models which need, big supercomputers that produce the actual trajectories for the tropical cyclones and hurricanes. And myself and my colleagues were delighted when our colleague, Suki Manabe, who developed really one of the first climate models for doing climate change, won the Nobel Physics Prize in 2021. It's really a great sadness to me that Lorentz never won the Nobel Prize. He died in, I think, around 2008 or so. Certainly should have won the Nobel Prize.